So when we look at precipitation reactions, we said that precipitation reactions exist in a state of equilibrium. Now there are some factors that will affect that equilibrium, or they will affect how much of our solid is actually capable of dissolving. Now, if I dissolve my salt in pure water, it's always going to have a greater solubility than if I have water that contains a common ion. So think back to Le Chatelier's principle. We said that if we add an ion that already exists on one side of my equilibrium or the other, it'll shift to counteract that. So if I have a solution that contains a common ion, I'm going to see this shift. So here I've got CeF3 breaking into Ce3 plus and 3F minus, and I'm given the KSP value. It says to calculate the molar solubility in pure water. So I know if X of that dissolves, 1-to-1 ratio between Ce and Ce3 plus, so X and X, 1-to-3 ratio between CeF3 and F, so this is going to be 3X. I'm told that KSP is 8.0 times 10 to the negative 16th. I know it's equal to my products raised to their coefficient. I'm ignoring the CeF3 because it's a solid. So now I want to solve for X. Well, if I look at this, 3 cubed, 3 times 3 is 9, times 3 is 27. 27. So 27, x to the third is just x cubed. This whole thing is going to be multiplied by x. So I'm going to have 27x to the fourth. Now if I divide both sides by 27, I get 2.96 times 10 to the negative 17th is equal to x to the fourth. Now when I plug this into my calculator, if I want to do the opposite of x to the fourth, I'm going to raise this to the power of 1/4. Now remember, depending on my calculator, I may need to put this in parentheses, but what I should get is x is equal to 7 let's see, I have 2 sig figs, so 7.4 times 10 to the negative 5th moles per liter of this can dissolve in pure water. Okay? But what if I don't have pure water? Now example 4 has a typo, so let's change this. This should be a common ion, not the same thing. So let's say instead of having pure water, I've got 0.2 molar cerium, Ce. Let's make that chloride, so Cl3. Okay. So now I've got this common ion. I've got CeF3. It breaks into Ce3 plus and 3F minus. I still want to figure out how much of this is able to dissolve. I know that this is still a 1-to-3 ratio, so this is 3x because it's 3 times as much. Now, because I've got a solution of cerium chloride, remember we changed that, I actually am starting with 0.2 molar Ce in solution. It's my common ion. Okay? So when I set up my KSP value, the KSP is equal, it's still 8.0 times 10 to the negative 16th. This is my product, so 0.2 molar times F minus, so 3x raised to its coefficient, 3. So I'm going to take both sides and divide by 0.2. So then I get 4 times 10 to the negative 15 is equal. 3 times 3 is 9, times 3 is 27, x cubed. So I'm going to divide both sides by 27. And then, because I've got x cubed left over, I'm going to take this answer and raise it to the power of 1/3. Okay? So what I should get, my new molar solubility is 5.3 times 10 to the negative 6th molar. So originally, in pure water, I was able to get 7.4 times 10 to the negative 5th to dissolve. Now, I can only get 5.3 times 10 to the negative 6th. A lot less is able to dissolve because I already have some of this Ce3 plus ion in solution. So by adding a common ion, I decrease the amount of my original solid that's able to dissolve. So take a second, solve example 5. Example 5, we still have this same equilibrium. We still have the same KSP. The difference is I have a common ion again. I'm dissolving 0.2 molar sodium fluoride in my solution. So this time I know that I've got 0.2 molar F minus ion already in solution. So solve for your molar solubility. Table 15.4 gives a lot of KSP values for us. Remember, a big KSP means a lot of my precipitate will dissolve, so we would say it was partially soluble, versus a very, very small KSP, so like 10 to the negative 30, 10 to the negative 40, means almost none of my solid dissolves. I would call it insoluble. Now, how do I determine whether or not a precipitate's going to form? I'm going to use something called a reaction quotient, Q. Now, we talked about Q before, and Q was telling us which way the reaction was going to go, whether we were at equilibrium or not. Same concept. Am I at equilibrium or not? Is a precipitate going to form? So, remember, the KSP tells me how much can dissolve. So under given circumstances, if my Q is smaller than the KSP, that means I've dissolved less stuff in solution than I can, so no precipitate will form. If my Q is bigger, then that means under certain circumstances, I've tried to dissolve more of each ion into solution than it can hold, and so a precipitate will form. So here's the way that KSP and Q work. So I'm told a solution is made by adding 175 milliliters of 0.10 molar barium chloride to 40 milliliters of 0.50 molar NaOH. Assume the volumes are additive. KSP for barium hydroxide is 5.0 times 10 to the negative third. Will a precipitate form? They give me the KSP for barium hydroxide. Ba is a 2 plus, OH is a -1, so my precipitate is BaOH2. So that tells me in BaCl2, I only care about the Ba2 plus ions that it's donating. In NaOH, I only care about the hydroxide ions it's donating. Okay? So I need to figure out my concentration of each of my ions in solution. So just with titrations, I'm told that I have 175 milliliters of BaCl2. For my concentration, I have 0.1 moles of BaCl2 for every 1,000 milliliters of BaCl2. Okay? Now I don't care about the whole thing, I only care about Ba. So if I have 1 mole of BaCl2, I'm going to make 1 mole of Ba2 plus. Now, in this case, this step wasn't super important. However, if I had cared about the Cl minus, this step would have been super important. So don't forget your last step, okay? So if I plug this into my calculator, I get 0.0175 moles of Ba2 plus. Now remember, I want the concentration in my entire solution. It tells me that volumes are additive. So I started with 175 milliliters of BaCl2. Since concentration's molarity, I'm going to go ahead and change that to liters. I added it to 40 milliliters of NaOH, so 0.040 liters. So that will give me my total volume of solution. Okay, so I get that I have 0.081 molar Ba2 plus. I'm going to do the same thing to figure out how much OH minus I had. So I was told I had 40 milliliters of NaOH. Its concentration is 0.50 moles for every 1,000 milliliters times, I know that if I have 1 mole of NaOH, it's also going to give me 1 mole of OH. So that tells me I've got 0.02 moles of OH minus. I need to divide it by my total volume. If you plug that in, you get 0.215 liters. So that gives me 9.3 times 10 to the negative 5th molar NaOH. So I want to solve for Q. Q looks just like KSP. So the concentration of Ba2 plus, which I said was 0.081 times 2, I know my concentration of OH minus, never mind, not times 2. So times 9.3 times 10 to the negative 5th raised to its exponent. So I plug that into my calculator. When I plug that in, I'm going to get a value. sorry, I screwed this one up later, so give me a second. 0.081 times 9.3 times 10 to the negative fifth. So I get 7.5 times 10 to the negative sixth. I was told my KSP is 5.0 times 10 to the negative third. Negative sixth is much, much, much smaller than negative 3 because Q is smaller than KSP. I will not have a precipitate PPT form. Okay, so I have to take the time to solve it out and figure out whether or not my Q is bigger or smaller to determine my precipitate. So take a second to solve example 7. I'm told I have 750 milliliters of CeNO3, 300 milliliters KiO3. This is the precipitate. I'm determining whether or not it'll form. And here's my KSP value.